Okay. So from our last meeting, I showed the derivation for the De Moivre's theorem. It's for the De Moivre's theorem, it simply means that if we have z to the power of, say, n, z to the power of n, where z is equals to the trig form, or cis theta, or cosine theta plus I sine of theta to the power of n. It's just simply equals to r to the n cosine n theta plus I sine of n theta. Okay. Now, let's say, for example, for this one here, we can expand the Cartesian form of this complex number, this one, by multiplying 1 plus I to the power of 6, meaning we are going to multiply 1 plus I 6 times. But it will be easier if we are going to do, or if we are going to use the trig form and applying the Moivre's theorem in our solution. It will take us less time to find the answer and also avoid making mistakes in our solution. So for example, for this one, transform this into trig form, where this square root of 2 is calculated using the modulus formula, where z is equals to the square root of x squared, and that is 1 squared plus 1 squared here, or that is the square root of 2. And then for the argument, theta is equals to our tangent of y over x. In this case, 1 over 1, or is equals to our tangent of 1, which will give us an angle of, in radian, pi over 4, or 45 degrees. So once we have the Cartesian form of the complex number into a trig form, we can then apply De Moivre's theorem to find the result when we have 1 plus I to the power of 6. Applying De Moivre's theorem, that this will be raised to 6th, the angles will be multiplied by the exponent. And so it will give us negative 8i. Expanding 1 plus I to the power of 6 will give us this result, and which also equate to negative 8i. Okay. Now, this is just a review of the previous topic that we did. You have, please check the rest of the practice questions here. Anyway, the solutions are found also in the slides given. Okay, and for the classwork, homework, please check Oxford book, and also the practice questions for 15F. Now, in the next topic, it's about complex exponents and roots of complex exponents. Now, remember, if we are multiplying two complex numbers in polar form or trig form, all we need to do is multiply the modulus and add the argument, right? So z1 times z2, this is just equals to r1 times r2. That will give us the modulus. And in terms of angle, we are going to add angle theta 1 plus theta 2, meaning the angle of z1 and the angle of z2. You can also do multiplication in terms of Cartesian form here, z1 times z2, which means this will give us negative 3 plus I, and then we have 1 plus I here, and do the expansion. Okay, so please answer this question, and check your solution after this. The answers or the solutions are in the slides here. Okay, so the success criteria for this next topic is, or are the following. You will write numbers with complex exponents in Cartesian form without using the trig functions. Second is to evaluate the complex exponents using Euler's form. So I'll be introducing this, this form here. So we have what we learned so far are complex numbers in Cartesian form. We also have what we call the polar form, or sometimes called trig form. And then another is in Euler form. So Cartesian form is z is equals to x plus iy. In polar form or modulus argument form, this is r cosine theta plus I sine of theta. This another form, the Euler's form, will be introduced to you in this part of the chapter. This is another form, third form. The third one is to represent the complex numbers on an Argand diagram. And lastly is to find the roots of the complex number. Okay. Now, this is what we call the complex, Euler form of the complex number. Remember, if we have z is equals to r cosine theta plus I sine of theta, cosine theta plus I sine of theta, we can write this one. So these two are the same, RCIS of theta. This is a shorter version. So the Euler form is R E I to the power of theta here. Now, before we will use, or before we will answer this one, let me show the derivation first. Why this is equals to this one. Okay. Wait, just open my notes. Okay, so this one here is just in the old curriculum. This is part of the options section. And we call this one infinite series, or the Taylor-Maclaurin series exposition for sine x, cosine x, and ex. Now, these following values of sine x is based from the Taylor or Maclaurin series expansion. Okay. I am showing this one because this will be used later on to show why RCIS theta is equals to RE to the exponent of I theta. This is what we want to show. RCIS of theta is equals to RE I of theta here. Okay. Now, from Taylor's series or Maclaurin series, I don't need to explain this to you because we will be doing this topic later on, and I'll in differential equation. So sine x here is equals to x minus x cubed over 3 factorial plus x to the power of 5 factorial minus x to the power of 7 over 7 factorial. Okay, so if we are going to extend this one, the shortened version of sine x based from Taylor or Maclaurin series is from 0 to infinity, -1 to the power of n, and this is x to n plus 1 over 2n plus 1, and this is factorial. For cosine x, this is equals to 1 minus x squared over 2 factorial plus x to the fourth, 4 factorial, minus x to the sixth over 6 factorial here. If we're going to expand this further, the shorter version of this expansion will just be equals to 0 to infinity, -1 here, n, and x to the power of 2n over 2n, and this is factorial. Now, for EX, the expanded form of EX based from Maclaurin or Taylor-Maclaurin series will be the following: 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. Expanding it, or the shorter version of it, will be the summation from 0 to infinity. And this will be x to the power of n over n factorial. Okay. Now, if we are to add this one and this will give us sine x plus cosine x is equals to 1 plus x minus x squared over 2 factorial plus, this is plus, minus x squared, and then we have minus x cubed over 3 factorial, and then we have plus x to the fourth over 4 factorial plus x to the power of 5 over 5 factorial minus x to the power of 6 over 6 factorial minus x to the power of 7 over 7 factorial. Okay. Now, if we are to compare now this result, this one, and this one here, the EX expansion, there is similarity in terms, except there is discrepancy in the signs, right? So if you will compare this and the expanded form of sine x plus cosine x, the terms are similar. It's just that there are discrepancies in the signs. So signs alternate in so the signs alternate in a way where pairs of terms alternate. And this is the property, or this property is a typical of powers of I. Remember, in powers of I, we have we have I. So example, I, and then another is I squared. And then we have I cubed. And then we have I to the fourth. Remember, this is I, this is -1, this is -I, this is 1, and then I to the fourth, this is 1, and then another will be a repetition, I, -1, -I, -1, which is the same as what we have here in the signs. So this suggests that expanding, declare this one. Okay. Now, this suggests that if we are to expand EIX, this is just equals to 1 plus IX plus I squared X squared over 2 factorial plus I cubed X cubed over 3 factorial plus I to the fourth X to the fourth over 4 factorial plus I to the fifth X to the fifth over 5 factorial, and so on. And now this will give us, using now, this will give us 1 plus 1 plus I squared x squared over 2 factorial plus I to the 4th x to the 4th over 4 factorial plus I to the 6th x to the 6th over 6 factorial. We are separating this one because this will give us I, right? And this will be plus ix plus I cube x cube over 3 factorial plus I to the 5th x to the 5th over 5 factorial and so on. Now, using the values of I squared here, this will give us I squared is -1, which means we can change this to minus x squared. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus, minus x to the 6th over 6 factorial plus, so in this side here, plus I, separating factoring I out, this will give us x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on. Okay. Now this gives us the expanded form. This is the expanded form of, so then therefore we can say, remember this part here is the real part. This one is the real part, correct? That's your real part. This one with the I, this is your imaginary part. This means we can then therefore conclude that EIX, this represents your real part in the trig function cosine x. And this represents plus I of sine of x. This one here. Because if you are going to review the video, this is equivalent to the sine x. This is equivalent to cosine x. Or the CIS of theta. So then we can say that, so therefore, E of IX is equals to cosine x plus I sine x, or you can say R, this time with the modulus now. EI, and then instead of x, we'll use theta. EI of theta is equals to R cosine of theta plus I sine of theta. Now, this one here, this is what we call the Euler form of the complex number. This representation of the number is actually considered to be the most beautiful because it contains everything. Remember, if we have, it contains all the number systems. I think that's what it's been described, the EI of theta. So what does that mean? EI of theta, or we will say this one, EI of pi, okay, where theta is equals to angle pi. This is equivalent to CIS of pi, or CI, cosine of pi plus I sine of pi. Now, EI of pi cosine pi is equals to -1 plus I sine pi is 0, or 0 pi. Okay, so therefore, EI pi is equals to -1 plus 0, or EI pi plus 1 is equals to 0. It contains all the numbers, a real number, an imaginary number, the Euler number, and so on. Okay, so I'm just showing this one because this is regarded as, I think, the most beautiful number or equation because it contains everything. There's another derivation for the Euler number, but I will not be showing it anymore because it will not make sense. Basically because It's using, we can also use calculus, chain rule to derive. But maybe I'll show that one later on once you are done with calculus. Okay? This result is considered to be, so we can write this one. This is considered to be aesthetically pleasant result. I of pi plus 1 is equals to 0. It's considered to be an aesthetically pleasing result because it contains all the fundamental operations, the addition, multiplication, and raising to a power, and also 4 constants of maths. We have 1, the constant of arithmetic. We have pi, the fundamental constant of geometry. We have E, the fundamental constant of calculus, and I, the fundamental constant of complex numbers. This one over here. Okay. Now, so again, let me go back to the slides here. Okay. So RCIS theta is equals to RE I theta. Now, if we are asked to find 3 to the exponent of I, okay, if you will check the solution here, we know that I theta means we express 3 as a power of E. So this will be E, and then we can remember in logarithmic, E to the ln is just the same as 3. So E to the ln of 3, and then we have I is just the same as 3 to the power of I. So that's why we have here E ln 3 to the exponent of I. We can move using rules of indices. We can move this one here in front, and then using the definition of complex exponential, that cosine of, because this is equivalent to cosine theta plus I sine theta. So in this case, this is your E theta here. So cosine of theta plus I sine of theta. Okay? So cosine, I think this is 1. I think this is 1. Sorry, this is not I, but 1. 3 to the power of 1. I think this is 3 to the power of 1. So moving now 1 in here, this will be E ln 3 or E theta. So we have cosine ln 3 plus I sine of ln 3. Now we can do the we won't be able to calculate this one manually, but you can calculate this using your calculator and use 3 significant figures here. Now come in, this is 3i, sorry. So I'm correct the first time. This is 3i. Okay? So because we know that R CIS of theta is equals to RE I of theta here. Okay? Now this 3i can be written as E ln of 3i. And then raising this will give us 3 I ln 3, meaning your theta here is equals to ln 3. This means your theta is ln 3. So RE I theta or EI theta. So in this case, this one here, your theta is ln 3. That's why we have ln 3 I sine of cosine ln 3 plus I sine of ln 3. Now, next is about the roots of complex numbers. This is what we call roots of unity. Let me show first why this is so. Let me show the so maybe it's better to show the derivation first. Okay. Okay, let's talk about the nth roots of a complex numbers. Nth roots of a complex number. Complex number. Okay. Now, if we have, say, w to the power of n is equals to z here. W is a complex number raised to some exponent, and we equate it to another complex number, a different one. So therefore, we can say if w is equals to 1 plus I here, is a sixth root, of z equals to negative 8i, then we will write this one as w, the power of 6, equals to z, or using the information for z here, the values for z and also w, this will give us, or we can write this problem, so this is an example, we can write this as 1 plus I to the power of 6 is equals to negative 8i. It's basically what we have here, this one. Okay. Or we can also say w equals to negative square root of 3 plus I is a 10th root of 512 plus 512 I root of 3. We can write this one as w to the power of 10 is a 10th root of 512. 512 plus 512 I root of 3, or you can write it this way, negative square root of 3 plus I to the exponent of 10 is equals to 512 plus 512 I root of 3. Okay, so that's we call the nth root or roots of a complex number. Okay. Now, how do we find the nth root or nth roots of a complex number? So how do we find? So how do we find the nth root? Find the nth root of or nth roots of the complex numbers. Okay. Example. First, let's let w here equals to s cosine alpha plus I sine of alpha be an nth root of z equals to r cosine theta plus I sine of theta. Okay, so w to the power of n is equals to z. Therefore, using the information that we have here, we can write this one as s cosine alpha I sine of alpha. This is wn. This is wn. To the power of n is equals to r cosine of theta plus I sine of theta. Okay, so I'm just rewriting this parts here in terms of the values of w and z. By De Moivre's theorem, we know that this n can be written as s to the n, and this will be cosine n alpha, I sine n alpha is equals to r cosine theta plus I sine of theta. So this is applying De Moivre's theorem. De Moivre's theorem. Now, okay, so again, if we have Wn is equals to Z, we can write this one as S to the N by using De Moivre's theorem, cosine N alpha plus I sine of N alpha is equals to R cosine theta plus I sine of theta. Okay. However, we know that two complex numbers are equal if their moduli are equal, and also their angles are equal, or their argument. So therefore, we can say that S to the power of N is equals to this one, R, or we can write it this way, S is equals to the nth root of R, or it's equals to R1 over N. Okay, just raising both sides here by 1 over N, 1 over N. This will cancel, and that will give us S is equals to R to the exponent of 1 over N, or writing it using this radical symbol here, this will be the nth root. Also, in terms of angle, the n theta, you can say that cosine n alpha is equals to cosine theta. And sine of n alpha is equals to sine of theta. Now we know that if we have cosine n alpha, cosine theta, the n alpha here for both sine and cosine. This implies that for both of these equations here, n alpha is equals to, n alpha meaning one rotation, is equals to theta, the angle, plus 2, depending on the rotation number, that will be represented by k, or 2 pi k, or 2 k pi, where k here is equals to either 0 rotation, meaning the first angle theta, 1 rotation, meaning k is 1, 2, and so on. This means this will lead to, let me just erase some parts here. Eraser. Just erase this part so we'll have some space. Okay. So this leads to this one here. This leads to alpha is equals to theta plus 2 k pi over n. Okay? Or this is equals to theta over n plus 2 k pi over n, where k is equals to 0, 1, 2, 3, and so on. Therefore, the nth root of a complex number can be written this way. So I need to erase because we don't have space anymore. So the nth root, or roots of a complex number, would be z is equals to r cosine of theta plus I sine of theta, and say z k here, meaning the root, for example, can be represented as the nth root of r. Of r, then you have cosine n over, theta over n. Theta over n plus 2 k pi over n plus I sine of theta n, theta over n plus 2 k pi over n. Again, where k is equals to 1, 2, 3, and so on, or 0, 1, 2. So as we can see here, the nth root, not n times, but nth root of r is just equals to r1 over n. And in terms of angle, consecutive roots differ. Consecutive roots differ by 2 pi n. 2 pi n, depending on the value of k here. So the difference from one angle to its next consecutive angle is it differs by 2 pi n. Let's have this example here to apply what I just discussed. The nth, when finding the nth root of the given complex number. Okay, so example, we have z is equals to -8 plus 8i. And we have to find the cube root. Or you say cube root z to the power of 3. Now, in terms of modulus r here, this is just equals to the root, 8 squared plus 8 squared, right? Or -8 squared plus 8 squared. And this will give us 8 root of 2, and that's your r. In terms of angle, because this is given in Cartesian form, tangent of theta is equals to 8 over -8 or -1. This means that theta is 3 pi over 4. Basically because this is -1. So it will be in the third, -1. Yeah, no, the fourth quadrant. Because y and x over y over x, positive y, negative x, the second quadrant. Okay. Now, to find now the root here, 8 squared, okay. So to find out the root, it will be w. We know that z of k, the root of the number, is equals to the nth of r cosine, and then we have theta over n plus 2k pi over theta over n plus I sine. You just delete this one. Just remember that this is 3 pi over 4. Sine, and this is plus, not plus, theta over n plus 2k pi over n. Remember, we have to find z to the cube root, meaning n here is equals to 3. So if we're going to use this equation, this formula, we know that this is equals to the nth root of n. So this is 3 of what is r? 8 root of 2. Okay, and this will be written as cosine theta over 3, because we have to find the third root, plus 2k pi over 3 plus I sine of theta over 3 plus 2 k pi over 3. Okay. Again, n here we have 3 because we need to find the cube root. Let me just erase some parts so we'll have some space. Now, okay, so from this part in the solution, this one here, remember, if we have the third root of 8 squared of 2, we can write this one as 8 to 1 over 2 times, to the exponent of 1/3, right? We can write this one. Correct. You can write it that way. It will be easier to manipulate the values. This means this will give us a result of 2, because this is the third root of 8, that's 2, and then 1 over 6. So this will be the sixth root of 2. Okay, so we can write this one now, this one into this one. Erase that. Okay, so again, from here, we can write this as 2, the sixth root of 2. And then let's just use the value of theta, if you still remember. Let's replace theta by 3 pi over 4. So cosine of 3 pi over 4 over 2, over 3, plus 2 k pi over 3, plus I sine of 3 pi over 4 over 3, plus 2 k pi over 3. Okay, which means where k here is equals to 0, 1, 2, 3, and so on. Simplifying this line of the solution, this will give us 2, the sixth root of 2, and the cosine theta here, this will give us cosine of pi over 4. Let's manipulate this one, plus 2 k pi over 3, plus I sine of pi over 4, plus 2 k pi over 3 here, where k is again 0, 1, 2, and so on. Just erase this. Okay, so again, for k here is 0, 1, 2, and so on. So now let's replace the value of k. So we now have the general formula for finding the roots of the equation. So when k is equals to 0, this equation here becomes 2, 6 root of 2, and this will be cosine pi over 4. This will be 0, so that will be 0 here. It will be 0 here. And then plus I sine of pi over 4, and that's the first root. When k is equals to 1, this will give us, so let's label this W1, or the first root. W2 as our second root, this will be 2, and this is 6 root of 2. So if k is equals to 2 here, this will be 2 times 2 is 4 over 3. So that is, k is equals to 1. Come on. K is equals to 1. So this becomes cosine pi over 4 plus 2 pi over 3 plus I sine of pi over 4 plus 2 pi over 3. Or this is equals to 2, 6th root of 2, and this is going to be cosine of, so pi over 4 plus 2 pi over 3 will give us 11 pi over 4 plus I sine of 11 pi over 4. Okay? Now, since we are, remember in the fundamental theorem of polynomials, of algebra, if we have 3, if we're finding the third root, we are expecting we have 3 roots here. So the next thing that you will need to do is just to find the value of W3 where K is equals to 2. So when K is equals to 2, let's find the rest of the last root. Okay. So okay. To find the last root here, K is equals to 2. Okay? Because we need to find only 3 because that's Z to the power of 3. When K is equals to 3, this will give us W3 is equals to same R2. We have the 6th root of 2 here, and then this will be cosine pi over 4 plus 4 pi over 3, because we will have K is equals to 3. So 3 times 2 is 6. 4 pi over. So when K is equals to 3, 3 times 2 is 6 over 3. Not K is equals to 3. K is equals to 2. When K is equals to 2, because that's K is equals to 1 here. When K is equals to 2, your third root is 4 times 2. 2 times 2 is 4 over 3. Okay? And then we have plus I sine of pi over 4 plus 4 pi over 3. And that's it. So all you need to do is combine the angles here, which will give us 19 pi over 12. So cosine 19 pi over 12 here, 19 pi over 12 there. So as you can see, 2 pi over 3, right? 2 pi over 3 is the difference between 2 pi over 3 is the difference between two arguments. Okay. Okay, so I guess that's it. We have found now the 3 roots W1, W2, and W3, where K there is from 0, 1, 2, because we only need to find 3 roots, because we have to find the third root of the given complex numbers. Okay. Now, if we are asked to solve the equation of Z to the power of 3, and the other side is 1. Okay? This is what we call the complex for roots of unity, I think, if I'm not mistaken. Now remember, Z here is x plus IY, right? So to find the modulus and argument, well, of course, this is x plus IY, right? So therefore, the modulus here, is 1. The argument is also 1, x plus IY. And that's equals to, because we don't have an angle here, this is 0. Okay? So again, take note that this is Z to the power of 3 is equals to 1. Z here is x plus IY. Power of 3 is equals to 1. So meaning the modulus here is also this modulus. The modulus on this side is equals to the modulus here. The argument on this side is equals to 1, which is equals to, we don't have the angle because this is just number, the real part. And we don't have the y, the imaginary part. So argument is equals to 0. Argument of 1 is equals to 0. In CIS form, you can write this one. Z is equals to R CIS theta. Or we can write this as R CIS theta to the power of 3 is equals to 1 CIS of 0. Using de Moivre's theorem, this will now be R to the power of 3 CIS 3 theta is equals to 1 CIS of 0. So therefore, from this result, we will have, so from this last line in our solution, this will give us R, so therefore, R cubed is equals to 1, correct? Or R here is equals to 1, right? Because if you're going to raise this 1/3, it's just equals to 1. In terms of angle, so 3 theta is equals to 3 theta is from 0 to 3 theta is from 0 to pi. Okay, come in. So 3 theta, we know that if it's 3 theta, 0 to, if it's theta only, then 0 to 2 pi, right? So if it's theta only, we know that that is theta is from 0 to 2 pi. If it's 3 theta, this will now be 0, 3 theta to 6 pi. Okay, now, let us find the roots here. Okay, so the roots, therefore, Z of 1 or W1 as we referred it before in the example. This is going to be, we'll use the 1, the R is 1, CIS of 0. Okay. So if it is theta 0 to 2 pi, if it's 3 theta, we will divide it. Theta will be 0, 0 divided by 3. And then we have 2 pi divided by 3. And then we also have 4 pi divided by 3. Because 3 theta is 0, 2 pi, and then we have 4 pi. Okay? 0, 2 pi, 4 pi. So CIS 0, Z1, Z2 is 1, CIS 2 pi over 3. Z3 is equals to 1 CIS 4 pi over 3. Okay? Or this is equivalent to in C1 CIS or cosine 0 plus I sine of 0. This is equals to 1. I'm just expanding the CIS. Cosine of 2 pi over 3 plus I sine of 2 pi over 3. And then we have equals to 1 cosine of 4 pi over 3 plus I sine of 4 pi over 3. Okay, let me just erase this part here so I can write some. Okay, now changing this into Cartesian form, we know this will be 1 cosine of 0 is 1 plus sine of 0 is of course 0. So I0 here is just equals to 1. This second part, the second root is 1. And this is cosine 2 pi over 3 is just equals to negative 1/2, if I'm not mistaken, plus I square root of 3 over 2. Okay, so now we can present the answer, the roots to this equation, in terms of its CIS form and also in Cartesian form. So Z3 here is equals to 1, negative 1/2, negative 1/2, and then minus I root of 3 over 3. So if we are going to plot this now into our argon diagram, just erase this part here so I can use this space. Again, Z1 is 1. Z2 is negative 1/2 plus I root 3 of 2. Z3 is 1/2 minus I root of 3 over 2. Plotting that one in the argon diagram. This is your Z1 because it's 1. Your Z2 here is negative 1/2, meaning negative x, positive y square root of 3 over. So this is going to be your Z2 over here. Your Z3 is negative 1/2 minus I root of 3 over 2. This is root of 3 over 2, not 3. So your Z3 is on this third quadrant. This is your Z3. Okay, so that's how we are going to plot the results, the roots of our equation. So again, as you can see here, they lie in the same circle, right? When we have z to the power of 3 is equals to 1, it means the third roots of unity. Okay? So if we have the third roots of unity, or z cubed is equals to 1, for example, it means that if you have z to the n equals to 1, it will have n solutions, depending on the number of n here. And the result will give us, let me just clear this one. So in the previous example that I showed, z of 3, the third root of unity, we will have, we call this one third root of unity. Third roots of unity. Okay? So if you have z to the n equals 1, it will have, or it has n solutions. Okay? It has n solutions. And it will have 1 CIS 2 pi over n, CIS 4 pi over n. And then if we are going to expand it further, CIS 2 and minus 1 pi over n. Okay, so this is what you will expect if you are to solve for the roots of unity. So depending on what number this is, so third, fourth, fifth roots of unity. Okay. Okay, so again, this one here, this is the problem that I showed you guys. Z to the power of 3 is equals to 1, giving our answers in the form x plus I1. So as you can see here, you'll have Z1 is equals to 1, Z2, Z3 here. And if you are going to plot that one, you'll have Z1, Z2, Z3. So the equation z to the power of n equals 1 will have n solutions. First one will be 1 CIS 2 pi over n, CIS 4 pi over n, up to CIS 2 n minus 1 pi over n. Okay, to solve for z to the power of n is equals to w. So this time now, it's not 1, but another complex number. The same as what I have showed in the example before the z to the n equals to 1. So in terms of steps, these are the things that you'll need to do. Okay, so first, write w, this part here. Need to write w in polar form, because I think this is given if this is given in Cartesian form. So you have to first write w in polar form, and then you will use the Moivre's theorem, this side of the equation, this part here, this one. Apply the Moivre's theorem because you have the exponent, okay, in polar form. Next is you will then compare the moduli, remembering that the moduli are always real. Compare the arguments, that adding 2 pi into the argument does not change the number. And then lastly is you will then write n in n different solutions in polar form. So like W1, W2, W3. Okay. If you are required to present your CIS result, okay, CIS theta in Cartesian form, then you have to do the conversion. Same as what I have shown in the example. So for this one, you can maybe use this practice. This is what I've shown already, an example previously on how to do this one. Try solving z to the fourth is equals to 8 plus 8 squared of 3i. Meaning, you have here z, x plus iy, to the exponent of 4. And you are calculating the 4 roots of the complex number. Then you'll see the solution here. Now, you'll also see in the practice questions, this one here, you will see the answers in the next slide. This one is in terms of Euler form. And I think I've shown this already, that if you have EI pi, meaning EI pi is equals to cosine pi plus I sine of pi. So just give the result. This one here is if your angle is pi over 2. Okay. Wait. Okay. So just a review on what we learned so far. I'll give the reasons why this is equal to this one later, but for now, so just a review on what we learned so far. So calculating the nth roots or roots of the equation of a complex number in number RCIS theta, that will allow us to find all complex numbers z that are solutions of the equation z to the power of n is equals to r CIS of theta. Okay, so again, to solve, say z is equals to alpha rho CIS alpha, and we have Zn is equals to R CIS theta. This will be rho CIS alpha. This is going to be Zn. Zn is equals to R CIS, and then Z is equals to CIS alpha. So we have rho Z, this is the Z here, correct? To the N is equals to R CIS theta. And then we apply the Moivre's theorem. And this will now be rho N CIS and alpha is equals to R CIS theta. Okay, so we know that modulus are equal. So rho of N is equals to R. And this will be rho is equals to the nth root of r. Whereas in angle, n alpha is equals to theta plus 2 k pi, or alpha is equals to theta plus 2 k pi over. So this will give us, so z equals to RCIS theta implies that z is equals to the nth root of r, and then we have CIS theta, not gamma, CIS, and then we have theta plus 2 k pi over n, where k is an element of a complex number. In Euler form, z to the n is equals to RE I theta, and this will give us z is equals to the nth root of r, e, so the angle now is theta plus 2 k pi over, okay, so, okay, so let's go back to this part over here, this one, this k point. So for that k point, where cosine theta is equals to EI theta plus E negative I theta. Now, we know that EI of theta is equals to cosine theta plus I sine of theta. Equally, if we have E negative I theta, that's just equals to cosine theta minus I sine of theta. Now, when you add EI of theta plus E negative I of theta, the resulting equation will be, you can try it later, plus E negative I theta. It's just equals to 2 cosine of theta, meaning the real part, twice the real part. And if we have EI of theta minus E negative I of theta, it's just equals to 2I sine of theta. These two properties here for cosine theta, sine theta, you can also, if you remember, this is also the same as twice the real part. There's a property previously where I showed that if we are going to add two complex numbers, x plus iy plus x plus iy, and x plus iy minus x plus iy, it will give you, so this is x plus iy minus x plus iy. The result will give you 2I sine theta. And if you have x plus iy and then plus x minus iy here, I think. Sorry, that's x plus iy minus x minus iy. The result will be 2I sine of theta. And if it is x plus iy plus x minus iy, this will give you 2 cosine theta. Because basically this will cancel out, right? I've shown the derivation for this one here. Okay, let me just refresh a little bit on that one. So if you have x plus iy plus x minus iy, meaning you're adding the conjugate, this will be, when you expand this one, this is going to be x plus iy minus x minus plus, sorry, plus, this is plus x minus iy. So this means this will cancel and you will have 2x or twice the real part. That's also the same with this one here, that if we have ei of theta plus e negative I of theta, this just equals to 2 cosine of theta. Or cosine of theta is equals to ei of theta plus e negative I of theta over 2. Which is also the same when we have x plus iy plus x minus iy, and then this is over 2. That's just the same. Okay? So that's the property here. Now you can check, or you may do the sine theta. This time it's just a subtraction. So the result will be twice the imaginary part. Okay? So you can see the solutions here for the questions given. The Euler formula to prove De Moivre's theorem, I think you'll be able, yeah, it's a very simple solution. So please try that one out. Okay. So I will make another video for this next topic. Okay, that's it for today, guys.